to find the relation between focal length and radius of curvature for a concave mirror. So what we'll do is, so first, so imagine you have a concave, so meaning it's a part of a spherical surface. So it's a concave mirror, so we shade it across like this. Then the center of the mirror, we'll call it as P, P being the pole. Alright, then what we have is we need to draw a principal axis. So this is the principal axis. Fine. Now in the principal axis, what we have is the center of curvature C and principal focus F. Now what we have is, so this part is important. So we have PF is nothing but F and PC is equal to R. Right. So these are the two things. Now what we are considering, we are trying to find a relation between F and R. Right. So let's imagine that we have some ray of light which is coming. It is coming parallel to the principal axis. So it passes through the principal focus. Right. So what we have, let's say it's coming from O and it reaches a point A which is on the mirror, and then it reflects back onto it. Now this is the given ray of light. Now what we have is, we are trying to find between F and R. So we have to use certain laws of triangle. Now we need to form a triangle. Now before that, what we do is, see this point C and point A. Now C is the center of curvature, right? So what we'll do is, we'll join A and C. Now why we are joining A and C is because if you join A and C, don't you think this is the normal? Right? Because C is the center and basically A is a point on the surface, so CA will be the normal. So what you have is, this angle and this angle will be the same because it's normal, so angle of incidence and angle of reflection. So you have OAC angle is equal to CAF is equal to, let's say, theta. So if these two are theta, fine. Now what we have is ACF angle. This will also be theta because angle OAC and ACF, they are alternate angles. So even this will also be theta. So this is also theta, this is also theta. Alright. Then if, see, we have in triangle CAF, we have two angles to be theta, right? So the exterior angle, that is angle AFP. So angle AFP will be 2 times theta. So what we have is, this angle is 2 times theta because the exterior angle is sum of opposite to interior angles. Right? Okay. So next what we do is, now from A, we drop a perpendicular onto the principal axis. Okay. Now when we drop a perpendicular, so we drop a perpendicular, let's say we name it as N. Now look at this, we have two important triangles here, that is triangle CAN and triangle FAN. Now in CAN, if you take tan of the angle theta, so you have AN divided by NC, and if you take tan 2 theta, so you will have AN divided by NF. Right? Now look at the figure, P and N are very close to each other, correct? So NF can also be written as PF, almost equal to that, and NC is almost equal to PC. So this changes to tan theta is equal to AN divided by PC, and tan 2 theta is equal to AN divided by PF. Now what is PF and PC? That's nothing but the focal length and the radius of curvature, right? Okay, so we'll substitute that. And one more thing, is for small angles of theta. So if theta is very small, very small, then tan of theta is almost equal to theta. So we have theta is equal to an divided by r, and 2 theta is equal to an divided by f. So you can substitute this theta as an by r. So we have 2 times an divided by r is equal to an divided by f. Now an cancels, right? So what do you end up with here? You end up with 2 by r is equal to 1 over f, right? So if you cross multiply and if you do it, you will get this as f is equal to r divided by 2. So this is what we get as the relation between focal length and radius of curvature. So half the radius of curvature is the focal length. So even if you look at the figure, f is almost in between P and C. So we proved this for a concave mirror. We'll try to do the same thing for convex mirror.